All right, so the first question, the fill in the table is just chlorine. So chlorine 37, this number always goes in the top left. It's the mass number. So you're going to write chlorine like this, 37 in the top. You're going to minus the number of protons to get the neutrons if you need them. So in this case, since there's 17 protons in chlorine, and there's always 17 protons in chlorine, because if you look at the periodic table, you're going to notice that the atomic numbers on this are in the upper left, and that doesn't change. If 35 changes to 36, you don't have bromine anymore, you have krypton. And so that number is never going to change. When you write them like this, you put it in the bottom left, the protons, rather than the top right in the periodic table. But when you subtract these, you're going to end up with the number of neutrons, which is the other part of the mass number. Now, with strontium-84, all this is telling us is, okay, so strontium-84 is the mass number that they use to name each of the isotopes. So as this number changes, the number of neutrons changes. The number of protons doesn't change, or else it would not be strontium anymore. So when we're talking about strontium-88, the reason that we know it's the most abundant is because we know that based on its average mass number, which if we look at it in the periodic table, wherever strontium is, ST, come on, 87.620, since we know there's close to the same amounts of 88, 86, and 87, we know if we take the average of that stuff, by abundance, we know the only way that 88, it's going to be leaning towards 88 as much as it is, like that. It's way closer to 88 than 87, so you know there must be more 88. Now, for this one with the X number 8, this is just a made-up element. They're just doing this to see if you get the concept of so what you do is you take each of those numbers that they gave. So they gave a mass of 325, 326. They gave 146, or no, not 146, sorry. Or was it 146? No, they gave 324, 325, 326. And so what I did was I times those by their percent abundance as a multiplier, not a percentage, 0.36 for 36%. And you get three numbers. And when you add those numbers together, you get the average mass by abundance. Antimony is SB. I know that's kind of confusing, but since they give us on the periodic table 121.76, we know that if there's only two isotopes of each of these, we know that the percent abundance, to figure it out, we'll say, okay, this is the average mass. This times what equals 122. And so to figure this one out, we're like, okay, so antimony 122.9, what was I going to say with that? This is strontium 123, and that's strontium 121. The reason why when we multiply 121.76 times x, I'm just doing the algebra to undo this average, because we know that to get this average, we started out with something plus something divided by 2, right? A plus B divided by 2 equals, and it gave us this, so I'm just undoing that to figure out what A and B are. So in this case, if I say this is A, what ends up happening is I get a percentage, and that percentage, let's see, 122.9042 divided by 121.76. Oh, I did it backwards. 121.76 divided by 122.9042. Well, I guess either way it's the same. So you either take this number, or you could take the first one I did and do 1 minus this, or this minus 1, sorry. But what this is saying is that since our number is way closer to, what's it way closer to? 121.76. We're slightly closer to this one. And so we know we should be getting, let me see. Why isn't this working? 121. Oh, that's right. Mike Russell, I think, did it like this. You have to do 120.9038 times its percent abundance plus 122.9042. I'm gonna have to post this on YouTube just to send it. Let's see. So this is going to give you, if we times it by its percent abundance, we're going to get some fraction of this amount. Let me do this. And this will be times, it's either percent abundance minus 1. I think that's right. And this will equal 121.76. It's a little bit more algebra than I wanted to do. But you should get around 40 or 50% for one of these, and then around 50 or 60% for the other. And you can kind of tell that it's like almost right in the middle of it's almost right in the middle of these two. And so all I'm doing is I'm multiplying this by some percent that we don't know, and then this times that same percent minus 1. If this doesn't work, try 1 minus this. And it should give you, when you solve for this percentage, you just do the algebra, and it should give you like 40, 50, or 60% for one of these, and then 40, 50, or 60% for the other. And when you add those 2% together, you should get 100%. For this last one, the table, like I said before, that's the mass number, that's the protons. We're just filling in the blanks. So 72 minus 32 is 40, so that's 40 neutrons, i.e. we're dealing with germanium 72, we already know that. There's no charge on this, like there's nothing like this. So we can assume there's the same number of electrons as there are protons. Atomic number 32, because that's the number based on the number of protons. The mass number is always that number up there, which is the sum of neutrons and protons.